We've got a prompt now that this meeting is now being recorded. You'll just get it. Okay, so let's start the normal distribution today. And without a doubt, I will claim that the normal distribution is the most important distribution in all of probability and statistics. Okay, now unlike our discrete cases, in continuous, we're not going to start out with experiments and then figuring out what kind of experiment fits a particular distribution. Okay, we're not going to do that job. We're just going to see how a distribution looks like, what's the density function, how does that look like, and we'll be provided this information that a particular problem fits the normal distribution, and then we need to tackle the problem using the normal distribution. Okay, so I'm going to write the PDF for that. Mu and sigma square have the usual meaning, which is the mean and variance. Now you will find that at places the parameters are written as mu and standard deviation and variance. It doesn't really make a difference. In the text as well, you have mu and sigma, which is a standard deviation, but variance is more prevalent, although it doesn't make any difference. Okay, so what we need is a random variable x with these two parameters under these two conditions, that there should be some variance and mean should be finite. Then we write the density function as follows. Okay, and E and pi have their usual mathematical meaning. Okay, so if any random variable follows this density function, then we claim that the random variable follows a normal distribution. Now, it's easier to see that the density function is always non-negative. Okay, one, we have this expression which is to the power of e, whatever this expression is, if it's to the power of e, it remains positive. Sigma, which is standard deviation, has to be positive. Pi is positive, 2 is positive, so the entire thing always remains non-negative. Yeah. One more thing, and let me write it here. So this is the prevalent way of writing that the random variable x follows the normal distribution with parameters mu1 sigma square. The tricky part is to show that when integrated over all possible values of x, this density function sums up to 1. Okay, now we're not doing mathematical statistics, so we'll skip the maths wherever we don't really need that. So we'll just take the word that this does sum up to 1. And if we follow the usual procedure of finding out the mean and variance, then for this density function, it can be shown that the mean will come out to be mu and variance will come out to be sigma square. You know the usual procedure now. You just multiply the density function with the random variable and integrate the product over all possible values of x. Uh, the normal distribution curve is perfectly symmetrical. And bell-shaped. It's not necessary that a symmetrical curve has to be bell-shaped. This one although is, and centered on its mean. So this is how it looks like. It's a little difficult to draw a perfectly symmetrical curve. Centered on its mean. Yeah. Now if I so both our normal curves, I've tried to draw them symmetrically. Let's try one more time. So this one, let's say, has variance mu square x This one has variance, sigma square y. So if we compare these two, we have this mu of y is greater than mu of x if I assume that the horizontal axes are same for both the diagrams. Okay, just to be clear, I'm not drawing the horizontal axis with this origin being 0. This is not the origin. It's the origin for the vertical axis starts with 0. I'm not claiming that the value at this corner is 0 for the horizontal axis. But assuming that the values are similarly plotted, then the mean of the second distribution is higher than the mean of first distribution, and the variance of the first distribution is greater than the variance of the second distribution. The higher the variance, the more flat the normal distribution curve is. The lower the variance, the more concentrated the distribution would be. Okay. Now from normal distribution, let's move to standard normal distribution, which is a very important tool to actually solving problems. Okay, now let's say it's a different color. Issue with normal distribution. When I say normal, I can also say non-standard normal, but that would be a little lengthy to write again and again. So when I say normal distribution, I mean it's not standard. So we have to do this. Okay, it is a continuous distribution. Then that means the probability that the random variable takes on any particular value is 0. Okay, there would be positive probabilities for intervals. So the computation of such a probability where we want the probability that the random variable x takes value between intervals a and b, between these two values. Now for this, we would need to evaluate this definite integral. Now, this would require some effort, and if you have to do it again and again, that would require a lot of effort utilized again and again. Now I have this tedious task of speaking sentences and writing sentences so that this set of notes becomes useful later on. Now it'll be useful to have pre-calculated tables for cumulative distribution for these sort of calculations. That will be very helpful. Okay, but there's an issue. The issue is that we would need many tables. Okay, all with different combinations of the two parameters of normal distribution. Okay. How do we get around this problem? We get around this problem by standardizing a random variable. Standardization is just linear transformation of the variable, which is we take the value of the random variable, subtract its mean from the value, and divide the entire thing by standard deviation. So Z defined as this. So you see I've specifically put subscripts to denote which mean and which standard deviation. Okay, how there's a particular property that every standardized variable, when standardized according to this method, then that is that its mean is always equal to 0 and its variance is always equal to 1. Okay, let's see. So if we take expected value of the standardized variable z, it should be same as expected value this. Since standard deviation is just a constant, it moves out and left with expected value of x and expected value of a constant mu of x. Both will be mu of x divided by sigma will be 0. Also, the variance of a constant, when it comes out, it will be squared because it's coming out from the expression for the variance. When a constant is subtracted from x and you want the variance of that expression, the constant really doesn't make any difference. And we have this, the variance of the standardized version. is 1. Let me also write this. That is just linear transformation of x. Now, how is standardization useful? Okay, and before that, let's just sort one more thing. If x is a normal random variable, then its standardized version according to the given expression is also a normal random variable.
Excuse me, sir.
Yes,
So, how is a standard normal distribution different from normal distribution?
I'll come to that. Give me a moment. So, the standardized version is also the standardized random variable also follows the normal distribution. The parameters take different values, and for every random variable, its standardized version has this property that mean is equal to 0 and variance is equal to 1. Okay. We have a special name for such a standardized random variable. We call it standard normal variable. And mu and sigma are the only two parameters of a normal distribution. If you have the same values for the parameters, you basically have the same distribution. Okay, so we only need one table, and let me say one pre-calculated table of values for a standard normal variable, and this will be for the cumulative distribution. Because the parameters are always the same. Mean is always 0 and variance is always 1. Now the question, how are these two different? Both of them look like this. So we have a curve for a normal random variable x. Okay, it looks like normal bell shaped, centered on its mean, and has variance equal to this. Okay, if I plot its standardized version with z being x minus mu of x divided by sigma of x, it's also going to look like a bell-shaped curve. Okay. But this will be centered on 0 and this will have variance equal to 1. Okay. Whatever the values of the mean and variance of the normal random variable x are. So whatever these values are, mu of z will be equal to 0 and variance of z will be equal to 1. Which means that the standard normal curve will be same for every normal random variable. Okay, now then what would be the difference? The difference would be in the correspondence in values in the horizontal axis of the two plots. So that's fine. For different random variables, the correspondence of values on the horizontal axis of two diagrams above will be different. Okay, how do we use this? Let's see. A little more. So let's say I have 2 points A and B here. Let's keep them further apart. A and B here. And I want this. The probability that the random variable takes on values between A and B. That probability would be the shaded red area. Okay, is this point clear? Are we clear on this? That this probability is the shaded red area. Okay. Now, There will be a corresponding point for A and corresponding point for B in the right panel. Hmm. And this shaded area. Let me use another color. Oh, fine. Okay. So if we want the probability in the left panel, which is the red shaded area, all we have to do is standardize the variable, find the corresponding two points. Let me also write this corresponding. So A and B. All we have to do is find the corresponding points A and B and calculate the purple shaded area. Okay. And how do we calculate purple shaded area? Let me again take this. Okay, if it's clear, we take this entire purple shaded area and subtract the green area from that. No, purple is not the right color for this. Let's use red. Okay, now why I'm doing this particularly in this way is that because we will have a pre-calculated cumulative table for standard normal. Okay, so let me use these terms z of a and z of b. If we want the probability that the random variable z takes values between za and zb, all we have to do is look at the standard cumulative standard normal table and we'll simply be able to figure out what the red area is. And then again look at the cumulative standard normal table, we'll figure out what the green area is. We'll can just take these two values and take the difference, and we'll get that. Now, is this making sense? How do we proceed? Any problems with this? Let me summarize again. So the problem would be we will be provided with any random variable. And when I say any random variable, that means random variable will take any values for mu and sigma square. Now, for problems such as calculating this red shaded area as a probability, we'll first transform the problem into standard normal. So the problem will get transformed from red to finding the violet, which is purple shaded area, and then we will visit the cumulative standard normal table to uh, finding the shaded area as I've shown here. Okay, so there is no need just to memorize the formulas. This is how the mechanism works. Mm. Now I'll stop for the day here. We will again have a theoretical class for normal distribution tomorrow, and then you can proceed with the questions. Let me stop recording at this point.